This is a continuation of our work with partial sums. We're going to move right on to exercise 3 here. Let a sub n equal 3 times 1/2 to the n minus 1 be a geometric sequence. And we want to find the first 4 partial sums for this sequence. We want to find some partial sums. We've been talking about what partial sums are. Notice that this is a geometric sequence. We, in the previous video, we just derived a formula to use. And here's my sheet from that formula. But, you know, that formula only applies to arithmetic sequences. So they have to have that particular type, right? An arithmetic sequence has that form that looks something like so. So we can use that SN formula here for that type. But this is geometric, so we don't have a formula. That's what I'm trying to say. When we don't have a formula, we can always just rely on what the basic definition is for a partial sum. So we're just going to crank these out by hand. The first 4 partial sums, S1 is equal to A sub 1. A sub 1 is 3 times 1/2 to the 1 minus 1 is 0. Anything to the 0 power is 1. So 3 times 1 is 3. I mean, a sub 1 just turns out to be that constant factor in front. S2 is equal to a sub 1 plus a sub 2. So that's 3 times 1/2 to the 0 is our a sub 1 plus a sub 2. When I plug 2 into my formula, I get 3 times 1/2 to the 2 minus 1, 1 power. So this is just 3, like we found before, plus 3 times 1/2 is 3/2. So that's going to be 9/2 when I add those up, or you could write that as a decimal if you want, 4.5. Okay, so I got S1, I got my S2, 2 more to go. S3 is A1 plus A2 plus A3, which is 3 times 1/2 to the 0 plus 3 times 1/2 to the 1 plus 3 times 1/2 to the, when I plug 3 into the formula, 3 minus 1 is 2, I get 1/2 squared. So this is 3 plus 3/2, just like we saw before, plus, now here's our new one that we have 3. Now that 3 whole is like 3 over 1, right? 3 over 1 times 1/2 squared is a 4th. So 3/4. So I got, let's see, 12/4 plus 6/4 is 18/4, 19, 20, 21/4. I got 21/4 here. And S4 is A1 plus A2 plus A3 plus A4, write it. A1 is that 3 times 1/2 to the 0 plus 3 times 1/2 to the first plus 3 times 1/2 to the second plus, for the 4th term, we'll have 3 times 1/2 to the 3rd power. So that's 3 plus 3/2 plus 3/4 plus, here we'll get 3 times 1/2 to the 3rd power, that's 1/8, right? So 3/8. Again, that's 3 over 1 times 1/8, or 3/8. And that adds up to 45/8. Check that ahead of time. And there are our first 4 partial sums for that sequence. Okay, now that's the idea of partial sums for a geometric sequence. We don't have a formula yet, but we're about to get a formula that we can use for any geometric sequence. And let's go ahead and derive that formula together. So what we're doing here is we're going to find a formula for partial sums of a geometric sequence that has the form. So we're starting with a sequence that has the form an equals a1 times r to the n minus 1 power, where a1 and r are real numbers. So this could be any geometric sequence at all now, not the one from the example. And we're going to start out again by, we're going to describe Sn, which we know is A1 plus A2 plus A3 plus dot 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 down the line to A sub n. And now I can rewrite that using the formula. I'm going to actually plug in now values of n. So when I plug in n equals 1, I get a1 times r to the 0 is a1 times 1 is just a1. When I plug in n equals 2, I get a1 times r to the 2 minus 1 is r to the first power. Then for a3, I get a1 times r to the 3 minus 1, or 2 power, plus all the way down the line, an will be the same, look just like that general expression for the sequence, a1 times r to the n minus 1. Now, what I'm going to do is something a little bit different from what we did with the arithmetic. I'm going to multiply both sides by something here, by r. So I'm going to take this equation and take r times Sn. And when I multiply all this by r, I'm going to have r times a1 plus a1r plus a1r squared plus dot 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 plus a1r to the n minus 1. This r on the right, I got to distribute to each one of those terms all the way down the line. So I'm going to have a1r plus a1r squared plus a1r cubed. So each one of those powers of r gets increased by 1 because I'm multiplying by r to the first. So r times r to the n minus 1 is now going to be r to the n. So r times Sn is equal to that. And now let's just, I'm going to call this, let's see if this shows up here, line 1, and I'm going to call this line 2. What I want to do is take 1 minus 2. I'm going to subtract. So I'm actually going to write Sn minus r times Sn. So I'm going to take everything in line 1 minus everything in line 2. So line 1 is that a1 plus a1r plus a1r squared down the line to a1r to the n minus 1. And when I subtract line 2, I'm going to have to subtract each one of those terms on the right. And I'm just going to line things up underneath. The first subtraction is a1r. I'm actually going to write minus a1r under this term here. Then I get minus a1r squared minus a1r cubed all the way down the line. Eventually, I'll have a minus a1r to the n minus 1. And my very last term, though, in line 2, right here, is going to give me a minus a1r to the n. Okay. So notice how all the terms have kind of shifted over by 1. So when I combine like terms here, I'll have an a1 all by itself, but now a1r minus a1r, that's why I lined them up in that way. Their like terms are going to cancel out. a1r squared minus a1r squared. Now you have to believe that there's an a1r cubed here that's going to cancel with the minus a1r cubed. Down the line to a1r to the n minus 1 is going to cancel out with, that's supposed to look like a minus a1r to the n minus 1. But then this one term is going to be hanging out the right, because I have one, I have the same number of terms in each line, so there's one extra one here, minus a1r to the n. That's all that I'm left with. So I have Sn minus Rsn equals that. Okay? And we're almost there. We're almost to our formula. I can now, I'm going to factor out Sn from the left-hand side of this common factor of Sn. So I have 1 minus R equals, I can also factor out A1. I'm going to factor it out on the left from these two terms, and I'm going to have a 1 minus R to the n. And now I'm going to divide both sides by 1 minus R. It cancels here, and I get Sn is equal to A1, 1 minus R to the n over 1 minus R. And that's our formula for the nth partial sum of a geometric sequence. So we got to keep in mind which formula applies to which type of partial sum, which type of sequence, right? And okay, so let's go ahead and do a problem. By the way, this cannot be simplified in any way if you're tempted to do any kind of canceling. You know, you can't cancel r's, they're not factors here. You have 1 minus r as a factor, but not 1 minus r as a factor above. So that's pretty much it. We got to work with the formula in that form. And let's go ahead and do an exercise here, exercise 4, where we're going to find the 10th partial sum of the sequence defined by an equals 3 times 1/2 to the n minus 1. And I'm trying to squeeze the formula there. And at the top, this is the same example that we just did moments ago at the beginning of this video, right? So we actually figured out the first 4 partial sums by hand, and so this is, you know, same as exercise 3 sequence. You could do this by hand if you really wanted to, but 10th partial sum, that's not that much fun to write out 10 terms and figure out all those fractions. It was kind of a fraction mess enough just to get 4. So what we can do here is, this is geometric. So we can use the formula for a geometric sequence right up above, and I'm just going to plug in. A sub 1 for this sequence, remember A sub 1 is 3, and our R is 1/2. So I have A sub 1 is just 3 times 1 minus, I have to take 1/2 to the exponent here matches the subscript on the s. So if it's the 10th partial sum, I need 1/2 to the 10th power over 1 minus 1/2. And now we got a little bit of work to do to rewrite this and clean this up a little bit. So we have 3 times 1 minus, now 1/2 to the 10th power involves 2 to the 10th power. That's going to be 1 over 2 to the 10th power. Now you can figure that out in your head, right? 2 to the first, 2 to the second is 4, 2 to the third, 8, 16, 32 is 2 to the fifth, 32 times 2 is 64 is 2 to the 6, 128 is 2 to the 7, 256 is 2 to the 8, 512 is 2 to the 9th. 512 times 2 is 1,024. 1,024 is 2 to the 10th power. 1 minus a half is a half on that denominator. Okay. And what I would do here is just write this out as follows. That 1 I can write as 1,024 over 1,024. Minus, just remember we're dividing all that by a half at the end. So I have 3 times, this is going to be 1,024 minus 1 is 1,023 over 1,024, all divided by a half. So I have 3 times 1,023 over 1,024. So it's like a whole number times a fraction. It's like 3 over 1 times that fraction. Divided by a half is going to be times 2, right? So 3 times 1,023 over 1,024 times 2 over 1. Just wanted you guys to be able to see that, which is going to be 6 times 1,023 over 1,024. And don't get all worried about reducing that. Let me just 1, 0, 2, 3. Times 6 is 6138. I guess there's a little bit of reducing we could do there. We could divide by 2 above and below. Bring it over here. 3,069 over 1,000. It's 512. 3,069 divided by 512. Yeah, I don't. 3,069 divided by 512 is about 5.994. I don't think the decimal does this much good here. There's the exact answer for the sum that we got reducing fractions. All right, I'm gonna stop here because we got a few more exercises to do, but we're gonna do them in a separate video. Let's just get this whole problem on here. There we go.